Okay, let's do linear now.
Okay. Okay, let's get started, please. We are talking about linear transformations. Linear transformations. Right, and so just can somebody remind me? Remember what a linear transformation is, or what does it do? What's good about it? What makes a linear transformation a linear transformation? Right, so you have remember it's some map, right, from one vector space to another, and it has two properties, right? Yeah. What are the two properties?
This sum of linear transformation to linear transformation this sum.
Right, so first that if you apply t to v plus w, then you're going to get t of v plus t of w. Right, maybe I should use u and v rather than v and w, or just v1 and v2. v1 and v2, right? And the second, that t of alpha v equals alpha t of v. Right? So these two properties, right, that the map takes a sum, right? The map of the sum is the sum of the maps. The image of the sum is the sum of the images, right? The image of the scaling is the scaling of the image. Right? These two properties together are called linearity. Right? We say that the map satisfies linearity. So today, a lot of the class is going to be exercises, actually. So the first one I want you to think about is this. If T1 and T2 are linear transformations, and B1 and Bn is a basis of V, then if T1 Bi equals T2 Bi for all I, then T1 of V equals T2 of V for all vectors in your domain. Okay, so in English, this says that if two linear transformations agree on a basis, then they are equal. Right? Then they're the same linear transformation. Any linear transformations that agree on a basis must be exactly the same linear transformation. Okay, so think about it. Right? You're going to need, you have only one, you have only two things that you can use, right? The linearity of your transformation. So it's got to be related to that. Think about it for a minute, and then we'll talk.
Could you remind me what the linear x form means?
That means transformation.
Okay.
It's just an abbreviation. Yes.
So the T1 and T2, the last line doesn't just say V's, right? So it's just like for any one V, T1 of that V equals T2 of that V.
Yeah. So what this is saying is that if for every, you have this basis, right? And you have that T1 of B1 equals T2 of B1, Right, T1 of B2 equals T2 of B2. They agree, their outputs agree on the basis vectors.
Yeah.
And what we're saying is that if that happens, then their outputs are going to agree for every input. Not just on those basis
Not just the
vectors,
basis.
but the whole
Yeah.
span of that basis, namely the whole vector space. Okay, talk to somebody behind you. Or you can talk to each other, right? No, you're gonna just sit two chairs away from me. Talk to each other.
Oh, just like. Expresses a linear combination.
No, I mean, like, because of, I think it's one which.
What you do is,
Describe them.
you know that T1 is the other. I think it's not out the office. You understand the property, you get office. T1 goes BI plus T2 BI in the office.
Okay, let's talk. So, right, you know that these two transformations agree on every element, on each element of the basis. You want to show that they agree on any element in your vector space. So, pick some guy in your vector space. What do you do? Well, you have to use this fact, right?
Yeah.
How do we work in the basis vectors?
Vector. It's like, you can express it as a linear combination.
Right. So, right, since B is a basis, we can express V as some linear combination, C1, B1 plus Cn, Bn. Okay. So why should T of this? Why should T1 of this be equal to T2 of this? Right? Well, T1 of C1, B1 plus Cn, Bn equals what?
T1, C1, B1 plus T1.
Okay, so you can use the first property and break this up, right? Because T1 of the sum is the sum of the T1s. T1 Cn, right? And then, Abel? Use a separate property, right? And pull out the constants. C1, T1, V1 plus Cn, Tn, Bn. Right? And then where do we go from there? Somebody other than Abel? Remember what we're heading for, right? We're trying to show that, right, T1V equals T2V, right? So at some point we better get T2 in there, right? We can do it because T1V1 is T2V1, right? So by hypothesis, right, let's call this thing. Let's call this property star, right? So by star, this is the same thing as C1 T2B1 plus Cn. Oops, that should not be a Tn, that should be a T1. Okay. And then what do we do? How do we get back to V? Go ahead, Abel.
We can retrace the steps and like.
Exactly. We retrace the steps in reverse, basically. Right? So we use property 2 to slide the constants back in. And then we use property 1 to combine them. Any questions? Okay. This would have been more concisely expressed with summation notation, right? Summation Ci Bi turns into summation T Ci Bi turns into summation Ci T1 Di, etc., etc. So it's more clean to do it with summation notation, but it doesn't matter.
Is it bad if you like combine the steps, like like 1 and 2, you know?
Well,
It's like frowned upon.
I mean, sometimes people write linearity combined together, actually.
Yeah.
They'll say like linearity means that T of alpha V plus beta W is equal to alpha TV plus beta TW. Okay. So in some sense, no, it doesn't really matter. It doesn't really matter, but I mean, as long as you know what you're doing, it's fine. But we did it this way just to make it clear. We're using this property, we're using this property. Yeah, I'd say it doesn't matter that much. Doesn't matter that much. Any questions? Everybody all right? Okay. Second idea. So we have again a linear transformation. We say T is 1-to-1. We say T is 1-to-1, or another term for that is injective. If T of V1 equaling T of E2, T of E2 implies that V1 and V2 are the same. So it's 1-to-1 if it has the property that whenever the outputs are equal, then the inputs must have been equal. Okay. You can't have two different inputs with identical outputs. Okay. So another way of saying this is that if V1 and V2 are not equal, then TV1 and TV2 must also be not equal. Okay. So that's logically the same thing, right? Whenever the outputs are equal, the inputs must be equal. Right? If you start off with different things, you're going to end up with different things. Okay, so let me start off with a non-example. Remember the map that we looked at a couple days ago? This one, right? Projection onto the x-axis. Right? This is not a 1-to-1 map. Not a 1-to-1 map, right? Because you could have two different inputs, but their output, right? Their output is the same, right? TV1 and TV2 are the same, but but the inputs were different. Right, the projection onto the x-axis is the same thing, but the inputs are not the same. Okay, so this is not a one-to-one map. You've seen one-to-one maps before in pre-calculus, right? When you talked about invertible functions, right? You have some function, right? Like the x squared function is not an invertible function, right? Because you've got -1 and 1 get mapped to the same height. Okay, so this is exactly the same notion as the thing that you saw in pre-calculus. Let's see. So for an example, let's start off with V an abstract vector space and V a basis. Okay. Then we have the coordinate vector map. Right? Let's call it P, say, that goes from V to Rn. Right? So the map that takes your vector to its corresponding coordinate vector. You all remember this? I hope you remember this, right? You have some basis, right? You have some basis. You take your vector, you express it as a linear combination of the basis, and then you take the coordinates corresponding to that. Remember that? Yeah, here.
Is that a vector space for V?
Yeah, V is a vector space. Okay. So remember, I'll say it again, right? The coordinate vector map, right? You take your V, you express it as some combination of the basis, right? And then the coordinate vector is those coefficients, right? You remember that? Coordinate vector is the coefficients that come from the unique expression of your vector as a linear combination of those guys, right? Unique because of the linear independence. Okay. So this is a one-to-one map, right? This is one-to-one, right? Because if you end up with the same coordinate vector, what does that say about your original vectors? Right? If W and V have the same coordinate vector, that means that they have the same coefficients. So that would mean that W equals C1 V1 plus Cn Vn, and then V also equals that. Well, they must be the same vector. Okay. So the coordinate vector map is a one-to-one map. Okay. So I'm going to give you an exercise. And so here's prove the following theorem. It's kind of a small theorem. So that T is 1-to-1 if and only if the kernel of T consists of just the zero vector. T is 1-to-1 if and only if the kernel of T is the zero vector. Okay, so try and prove, one way or the other. Take a minute or two and see if you can make headway on one or the other direction or both. Okay, talk with each other. Say something. Okay, let's think about the forwards direction, right? So suppose you know that t is 1 to 1, right? That if the outputs are equal, then the inputs have to be equal. Okay, why should that imply that? So you want to show that the kernel is the zero vector, right? What's the kernel? Somebody remind me what the kernel is. What?
Takes it to 0.
The things that t sends to 0, right? So you want right. So what we're saying is that we want to show that that 0 is sent to 0, and that it's the only thing that's sent to 0, right? So i.e. we want to show that t of 0 is 0, and that nothing else is such that t of b equals 0. Okay, why is t of 0, 0? We did that last time, right? That was the first boring fact from last time, right? So we know already that t of 0 is 0, right? Because t is a linear transformation. Okay, we said any linear transformation always sends 0 to 0. Okay. Okay. So why? How do we know that that's the only thing that's sent to 0? 110.
If it's a one-to-one function, we don't only have one output and an input.
Right. So only one output per input. That's
So t of anything can have
there's only one input that will have that output.
Yes.
Yeah, you said it backwards. Yeah.
Sorry.
There's only one input that will give you that output, right? That is, if another guy got sent to if another guy, so if t of b equals 0, then since t of 0 is 0 and t is 1 to 1, then b must be equal to 0, right? Right, because then these two guys would have the same outputs, and so the inputs must be the same. Okay. Or another way of saying that is that if we took anything other than 0, then it's not going to get sent to 0, right? Anything not equal to 0 would not be equal to 0. The output would not be equal to 0. Any questions? Okay. How about the reverse direction? The reverse direction is maybe a little harder. So suppose you know that the only thing that gets sent to 0 is 0. How do you show that t is going to be 1 to 1? Okay. So we start off with saying, suppose that t of v1 equals t of v2. Okay. And we want to see that then v1 equals v2. Right. We want to show we want to show that this guy is 1 to 1. In other words, when you start with equal outputs, you end up with equal inputs. Let me just write that out. We want to show if t of v1 equals t of v2, then v1 must be equal to v2. So suppose t of v1 equals t of v2. Okay. Anybody have an idea? If not, I'll ask leading questions. Anybody have an idea? Okay, so we have only one fact that we can use, that is the only thing that's sent to 0 is 0. Right? The only thing that's sent to 0 is 0. Okay. How do we use this fact about 0 to say something about TV1, to combine with TV1 equals TV2? Can you make something that's sent to 0 out of this fact? TV1 equals TV2. Can you say T of something is 0? Since TV1 equals TV2, T of la is 0.
0?
Somebody saying it? T of 0 is 0. Well, yeah, but that's not, that's
T1
boring.
minus
T1 minus
V2.
V2.
Yeah, T of V1 minus V2 equals 0. Right? Right, by linearity. Right, so you see, right? We get that T of V1 minus T of V2 equals 0. But that means that by linearity, T of V1 minus V2 equals 0. Right? But since the kernel of T is the 0 vector, that says that V1 minus V2 must be the 0 vector. Right? The only thing set to 0 is the 0 vector. Right? The kernel of 0. Right? The only thing set to 0 is the 0 vector. So that tells us that this V1 minus V2 must be the 0 vector. That tells you that V1 must be V2. Yeah, one time.
If V1 minus, how does V1 minus V2 become the 0 vector and V1 equals V2? Like, what if they were both the same vector? Wouldn't one minus the other just be the 0 vector?
When V1 minus V2 equals 0, you just add V2 to both sides, and you see that V1 is equal to V2.
Right. Okay. Oh, okay.
Yeah.
Wait, isn't that we got rid of the T?
Okay, yeah, so T of V1, V2 equals 0. I'm sorry, T of V1 minus V2 is equal to 0. And remember what we're starting off with, right? We start off from here, the kernel is 0.
Yeah.
Right? That the kernel of 0 means that,
So-
that the only thing sent to 0 is the 0 vector.
Yeah.
Right? If this thing is sent to the 0 vector, it must be 0 itself. Okay, so V1 minus V2 must be 0. Is that okay? Everybody all right? Everybody all right? Okay. Another important notion is something called onto. Okay. It's sort of the counterpart of one-to-one. Okay. So if you have a linear transformation again, a linear transformation. If T of V equals W, right, that is the image of T is all of W, right, the image of T is all of W, then we say that T is onto or surjective. Injective, surjective. If you're both injective and surjective, then you're called bijective. But we'll get to that in a minute. So again, let me start off with a non-example, and it will be the same non-example. So t of xy being x0, right? If we think of this guy as a map from R2 to R2, right? It is not onto. Okay, right? Like if I think of this guy as a map from R2 to R2, right? Then I don't hit every vector in the target space, right? Like I can't get this vector here, right? I can't get that guy as an output. I can only get vectors on the x-axis, right? So my image is not the entire target space, right? I don't cover all of R2, so I'm not onto it. Okay, not onto it. Because T, right, the image of T is not all of R2. Okay. For an example, we can look at one of those rotation guys. Right, that actually is onto. Right, because if I want to get this vector, well, I just rotate it theta degrees this way, theta radians this way, right? And then when I apply t theta to it, it gets rotated back onto that guy. So I can, whatever vector I have here, I can get it as an output of my transformation. Okay, so this actually is onto. Right. Here, there are a lot of vectors that I can't get as outputs, right? Right. I can't get this as an output. Can't get this as an output. I can't get, there are lots of vectors that I cannot get as outputs, right? And here, no matter what vector you give me, I can get it as an output. Is that clear? Everybody got it? Okay. I should say that it's a little bit subtle. So there's one subtlety. If we think, so coming back to this example, if we let V be R2 and W be the x-axis, we let W be the x-axis, right? That subspace, right? A subspace in R2. Then this guy, oops, is onto W, right? If we consider it from V to W, right, is onto, right? It is onto because, right, we can every vector in the x-axis I can get as an output. Right? So it actually depends on how you're defining your domain and range. Okay. If I'm thinking of this as a map from R2 to R2, it's not onto, right? Because I don't get all of R2. But I'm thinking of this as a map from R2 onto and into the x-axis. Well, then it is onto, right? Because I do get every element of the x-axis as an output. Okay. 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 Let me. Okay. Everybody, all right? So. Another example of, if we go back to this thing, the projection map, the coordinate vector map, so coordinate vector map, right? Taking your vector to its to its corresponding vector. Right? This is onto. This map is onto, right? Because if I want some output, well, I'll just make a vector that has that output, right? I just go back here, put together a linear combination. Well, that's the guy that has this output, right? So given this in Rn, just let B be C1 B1 plus C of Bn. Then P of B is C1 through Cn. Right? So given any vector over there, I can find a vector that gets mapped to it. Given any coordinates, I can find a vector with those coordinates by making it. Okay. So this map is also onto. We said it's also one-to-one. Okay. So it's both one-to. It's both onto and one-to-one. That leads us to the last definition. So if you have a map, again, you have a linear transformation. If T is one-to-one and onto, then we call it an isomorphism. We call it bijective. Okay, we call it an isomorphism, and we say that, B is isomorphic to W. And you write this funny symbol. Right? You write this equal sign with a twiddle above it. B is isomorphic to W. Okay, so coming back up here, coordinate vector map is an isomorphism. So our vector space is isomorphic to Rn. Okay, isomorphic to Rn, right? Any n-dimensional vector space is isomorphic to Rn. Okay, we're not going to say too much about this sort of map, but there's one thing that there's one theorem that I do want to give you, but we're not going to prove it. I'm just going to give it to you as a fact. Okay, so so T is an isomorphism if and only if there exists a linear transformation T inverse going from W back to V such that T composed with T inverse is the identity on W, and T inverse composed with T is the identity on V. In brief, people say, in other words, there exists an inverse linear transformation. Yeah, Ethan.
So what is the ID?
IE means that is ID, the identity, sorry. The identity map. So the map that doesn't do anything. Like the, sorry, I guess we've never seen it before. So if I write like ID, it's the map that doesn't do anything. Right, like the identity matrix, right?
Right.
When you multiply by the identity matrix, nothing happens. ID means the identity transformation that just gives you give it V and it gives you V right back.
Is it on?
Yes, somebody's
I have
talking.
an unrelated question.
Okay.
Then what does ID underscore W?
Yeah. So just think. So, maybe it's clearer if I put a composition map here. Is that clearer? So go back to take your minds back to pre-calculus, right? You have the composition of functions, right? You've composed functions. F composed with G is F of G of X, right? G composed with F is G of F of X, right? G of F of X, right? You've got inverse, back in calculus you have some inverse functions. F of F inverse is just X, right? When you take F of the inverse guy, you get X. When you take F inverse of F of X, you get X, right? When you compose them in either the inverse, if you remember your inverse functions from pre-calculus, when it was an inverse function, if you composed it, then nothing happened, right? That's all we're saying here. That there's F. It turns out that if T is an isomorphism, that is equivalent to there existing an inverse linear transformation. So it's got the properties that your old inverse functions had, but it's also a linear transformation.
Okay. So T times T inverse is just mapping V to W back to V.
Yeah.
Okay.
Yeah. So T inverse, right, goes from W to V back to W, so you get the identity map on W.
Okay.
This is the identity transformation on W, right, going from W to W. This guy is going from V to V.
Is onto and one-to-one like a property of T, or is it like, does it kind of depend on what you're mapping to from?
So yeah, that's this thing here. Right? So it's sort of both, right? Right here, right, you've got your map, but if you think of it as going from here to here, it's not onto. From here to here, it is onto.
Okay.
Okay.
Yep.
So yeah, it depends on the domain and the range as well. Yeah.
Why does T inverse go to W instead of V?
So T inverse, right? Think like this. How does your composition map go? Right. T inverse will take somebody in W, and then give you back something in V. You feed that into T, right? That will take it from V to back to W. So this guy in W ends up in W again. Okay. So the main thing you want to see here is that if your function is an isomorphism, then there's an inverse map. Further, that inverse map is a linear transformation. This is actually the interesting part. Okay, that map is a linear transformation. The fact that there exists an inverse map is just pre-calculus. The interesting thing is that inverse map is forced to be a linear transformation. Okay. The inverse map is forced to be a linear transformation, and that's the slightly tricky part about this thing. Okay, just give me 1 minute, and I'll prove one last result that I was hoping to get to. So you have a square matrix. Here's the theorem. Let A be a square matrix, and T sub A as before. Right? So T sub A is the left multiplication transformation. Right. So T sub A goes from Rn to Rn. Then T sub A is onto if and only if if and only if A is invertible. I'm just going to prove this. I was going to give this an exercise, but we're out of time, so let me just give the proof. Okay. So if T sub A is onto, that means that you can get any B in Rn as A times something, right? For some A times V is for some V in Rn, right? No matter what kind of target space you have, I can realize it as A times something, right? As T times V. Right? Right? But that means that the column space of A is all of Rn. Right? The column space of A is all of Rn. In other words, that the rank is n. But if the rank is n, that means that the nullity is 0. Right? But that's the same thing as saying that A is invertible. Sorry to rush through that at the end. That's it for today. Have a nice break, everyone, and thanks for coming.